Feeling good about this? Okay. All right. So I'm trying to make it as simple as possible. It's still multiples of cosine and sine, interestingly, because you get e to the I stuff, e to the I, and that's, you know, Euler's formula, cosine plus I sine. Yeah?
This is only for cases where it's a plus bi and a minus bi. What if they're both a plus bi and c plus bi?
They won't be. How do I know that?
Yeah, how do you know that?
Well, you can see what, like,
Every occurrence of a complex solution to a polynomial equation will occur in conjugate pairs. So it will be a plus bi, a minus bi. We saw the case before where we didn't have a real part, we just had plus or minus I. You can think of that as 0 plus or minus I, right? So the real part of that number is 0, and interestingly enough, if you put the real part in here, e to the 0x, that's just 1, and you get the rest of it.
Okay.
Yeah.
You go back.
Oh, yeah.
oh, never mind, sorry, that's the other one.
Okay.
Are we ever going to need, like, whatever beyond the quadratic formula for, like, r cubed if we're going to be doing higher weight?
Oh, no. No.
I just want to make sure.
So I think any problems, you know, that you get, if they're not factorable, it's not going to be, oh, I need the cubic formula, you know, to solve a general cubic. It gets complicated, and there's nothing for 5th degree and higher. There's no general formula to find the solutions of it. Yeah. Okay. So quadratic, probably all you need. No. If it's third, hopefully some factors out. They arrange the equations nicely, so sometimes factor out, then you got a 0 left. Yeah, 0 or 1. All right, so that's, you know, we touched on some stuff, 3.1, definitely 3.2, but so our work with second order linear differential equations translates nicely. That's subjective, nicely. But it can be generalized to higher order. Linear. So we are specifically dealing with linear of the form, you know, nth derivative, y nth derivative plus, and these are coefficient functions, p1 of x, y, and that's not y to the n minus first power, that's the n minus first derivative. So highest derivative nth order, plus, and who knows how many terms there are, but p sub n minus 1 of x, y prime, plus p sub n of x, y equals 0. So specifically, we are focusing on homogeneous. Okay. Theorem 4. Theorem 4 in the book, that's page 168. A lot of these things get translated nicely. And what it says that if we have y1, y2, dot, 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 y sub n. So for an nth order, to find the general solution, I would need n linearly independent solution functions. Okay? So if somehow we are able to come up with n linearly independent solutions, then the general solution is guess it's going to be a lot like it was before, but any solution, the general solution will be linear combinations of those. C sub 1, y sub 1 plus C2, y sub 2 plus sub n, y sub n. Okay? So that theorem goes both ways. Now, without linear independence, if I had any number of solutions, right, to the original equation above, then any linear combination is also a solution. But in reverse, if I have n linearly independent solutions, then any solution to that equation can be written in that form. So for appropriate values of the coefficients c sub 1, 2, 3.
Since there's more than just two solutions, how do you tell if they're all linearly independent without you? Because the Wronskian you taught us was like 2 by 2.
Right, right. Well, you're right on it. Yeah. So the question was, how do we check for linear independence when we have 3 or more?
All right.
So linear independence of multiple solutions. Solution functions? Okay, sure, I'm gonna make that up. Yes, the Wronskian can also be used with more functions than just 2. Yeah, it sure is. All right. So the Wronskian, like Wronskian of 2 functions is a 2 by 2 matrix. Well, it's determinant of a 2 by 2 matrix. If I have 3 functions and I want to check linear independence, then we'll have a 3 by 3, and I'll have a 3 by 3 matrix.
N by N matrix.
Yeah, 3 by 3 if I have a 3rd order. If I have a 5th order, it's going to be 5 functions, and they're 4 derivatives, so 5 by 5 matrix, and we're not going to do those by hand at all. But we're going to use the nth order Wronskian. Yeah. So the Wronskian, W, and if I have y sub 1, y sub 2, dot, 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 up to y sub n, yeah, it is going to be the same type of deal, y sub 1, y sub 2, dot, 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 y sub n. And then their derivatives, y1 prime, y2 prime, y sub n prime. And that's my first row is the 0th derivative, the second row is the first. So in the last row, it's going to be the n minus first derivative, y sub 1, n minus 1, y sub 2, n minus 1, y sub n, n minus 1. Okay. Now, yeah, to put your minds at ease, we will not do anything larger than a 3 by 3. Okay, that's a guarantee. So let's see how we would do a 3 by 3. All right. So just showing, say we had done the work and we had solved, found 3 solutions to an equation, and we want to check to see if they're linearly independent. So say those solutions are e to the x, and something as simple as e to the 2x, and y sub 3 equals e to the 3x. And we want to determine if these are linearly independent or not. Okay. If they are, then the Wronskian is not identically 0. So that's kind of what we're looking for. The Wronskian y1, y2, y3 is not equal to 0 identically, I should say, right? It could be 0 at points, but at least so long as it's not 0 over every number in the interval that we're interested in. And in parentheses, I'm just going to say they would be dependent, a dependent set of functions if the Wronskian does equal 0 for all x. All right. So how do I set this up? All right. So we lay down just the three functions in the first row: y1, y2, y3. So we got e to the x, e to the 2x, and e to the 3x. Okay. And in the next row, we just have the first derivatives. So first derivative e to the x, e to the x. First derivative e to the 2x, 2e to the 2x. First derivative this one, 3e to the 3x. And then there's second derivatives. E to the x, 4e to the 2x, 9e to the 3x. Okay, now this is going to be a little bit different. If you have not taken linear algebra, and again, this is not a linear algebra class, but we will be using methods from there. Okay, so when we do that, I'll explain at least the process, if not the theory. Okay. All right. So the way we do a 3x3 determinant, well, I can expand. Basically, I just need to expand it along one of the rows or one of the columns, and it doesn't matter which I choose. I can choose the easiest one if I want to, but I don't know which one's easy. I could do the
You get
easiest.
zeros, you fix those.
What's that?
Sometimes if you have a set of
If you have a 0 in one of the rows or columns, you can use that row or column because it's nice to have a 0 in one of those spots. But every entry in this has a sign associated with it. Top left corner plus, minus, plus, and it alternates. So minus, plus, minus, plus, minus, plus. It's just a grid of plus and minus. So when we expand it, that's going to become part of the coefficient. So I'm going to expand it just along the first row. Okay. So when I expand along the first row, I'm going to start with e to the x. I'm going to cancel lightly, use pencil, cross out the first column and row that involves e to the x, and it's a plus, so I'm going to keep that in mind. I'm going to have e to the x times the Wronskian of the 2x2, what's left when you cancel out the first row or column. So I'm going to have 2e to the 2x.
And why is that plus? Because you started off with top.
Start off as a plus, top left corner.
Okay.
And then, so I got 3e to the 3x, 4e to the 2x, 9e to the 3x. Okay, now, when I move to the next one, I have to remember that the sign alternates. Oh, let's use this. All right. So I'm expanding along the first row, so my next entry is going to be a negative. Okay? Or just minus. You can just remember that it's going to be positive, minus, positive, minus. All right. So minus, and I'm going to choose the e to the 2x. And cross out the column and row in which that appears, and then you'll have 4 entries left over. 2x2 Wronskian of those. E to the x, 3e to the 3x, e to the x, 9e to the 3x. Am I going to have enough room?
I'm sorry, why did you choose e to the negative 2x?
Oh, I'm expanding along the first row. You could also do a column. So I'm choosing these guys, and it's going to start off plus, minus, plus in those terms. You could also expand it along any column you want.
Oh, so you just do one of these. You're not doing this with every single.
No. One row or one column.
So it's like the cross product.
Yes.
Okay.
Yeah. Cross product also used. Yeah, you can arrange it just as a determinant of a matrix.
I think we will.
All right, and then my last term plus, and I'm doing e to the 3x now.
Would it be possible to, like, instead of doing a row or a column, do a diagonal?
It's
No,
a good question.
you can't, right?
I
Probably not.
I
You
don't think
can't.
so.
Let's give it a try.
No, you can't because that won't.
Yeah, it would mess up
have
the
to.
signs.
Yeah.
You could also just put this in your calculator process.
Yeah, you can put functions in there, yeah, great.
Yeah.
Calculate yourself up.
All right, so I want to show you, instead of just punching in the calculator, how it works, but and if you guys want to do that, that's great. E to the x, 2e to the 2x, e to the x, 4e to the 2x. So same thing, just finding the determinant of a 3x3 matrix. It's called expansion by what? Minors, using minors or cofactors.
Is this, cofactor expansion?
Cofactor expansion, yeah. All right, so here I got my e to the x. Now when I have it reduced to a 2x2, we just simply do our diagonals. That's going to give me 18 e to the 2x times e to the 3x. And I add those, when I multiply, I add those. 2x plus 3x is 5x. Minus this one, that's going to be 12 e to the same power, 5x, minus e to the 2x, giant parentheses, and do the Wronskian of this 2x2. 9 e to the x times e to the x times e to the 3x is e to the 4x, minus, and multiply this diagonal, we're going to have 3 e to the 4x, plus e to the 3x, and this is going to be what, 4 e to the 3x, minus 2 e to the 3x. All right, not so bad. Now, the good thing about it is when I do the Wronskian and each separate one, look at those powers are the same. So I got like terms here. What I have is 18 e to the 5x minus 12 e to the 5x. That gives me 6 e to the 5x times e to the x. So that's going to be 6 e to the 5x times e to the x, 6 e to the 6x. Minus 9 e to the 4x minus 3 e to the 4x. That is going to be 6 e to the 4x times e to the 2x. So that's 6 e to the 2x times e to the 4x and e to the 6x. Uh-oh. That's a 0, but I got one more term to go. Hopefully that doesn't. Anyway. Same thing here, so I can combine these. This is a minus, so I got 4 e to the 3x minus 2 e to the 3x. That's 2 e to the 3x times e to the 3x. That's 2 e to the 6x again. These guys cancel each other out, don't they? We just get 2 e to the 6x, which is never 0. Okay. So what that means is they are linearly independent. Okay. And linearly independent, you know, the thing about the book provides a lot of detail. If you're interested in knowing what it means for 3 or more functions to be linearly independent over an interval, great, read about it. It basically means it's kind of similar. Well, instead of one being a constant multiple of the other, that's 2 functions. One way to think about it is none of those functions can be written as a linear combination of the others, right, where C1, C2, or C sub n are my coefficients. No single function can be written as a linear combination of the others. Okay? Or, alternately, n functions are linearly independent if this equation, oops, C sub 1, F sub 1, so n functions, call them F1 through F sub n, C2, F2 plus C3, F3, whatever, C sub n, F sub n equals 0. If this equation, if the only solution to this equation that's a linearly independent set of functions. If the only solution to this equation is if you take all the coefficients to be 0. An alternate way of thinking about that is that none of these functions can be expressed as a linear combination of the remaining n minus 1 functions. Okay, but not terribly important. We just need them to build our general solution. So let's take a break. Sorry, we went a little long that first section, but let's take 10 minutes.